This presentation is by Dr. Kevin Jorissen, Distinguished HPC Cloud Architect with Oracle Cloud. Now, the subject of discussion right here, the new era of HPC, data-driven, real-time in the cloud. Here, ladies and gentlemen, is Dr. Jorissen.
Thank you very much. So my name is Kevin Jorissen. I do high-performance computing for Oracle, and I'm talking to you today from Seattle, where, as you can see behind me, it is already night. But I'm very glad to be here with you today. I'm going to go right in. Oh, could I have the next slide, please? And no more. Okay. I'm going to go right in and tell you about one of the most exciting projects that I'm involved in at Oracle now. We recently started sponsoring Red Bull Racing, and if there's any Formula One fans listening, then you'll know that it has been a very exciting last season. And not only do we sponsor, but here are two types of projects that we are doing with Red Bull Racing that illustrate very well, I think, the more traditional way of doing HPC versus the modern way of doing HPC that is more a trend for the future. So on the left, Red Bull is working on design for a new engine. Of course, race cars have to be a little faster and a little better every year. You do that by improving the engine. And that's a very well understood classical problem. It's the design of a vehicle, which you do by modeling the workings of the engine, the airflow over the vehicle, the structural changes in the event of a crash, and so on. On the right hand is a very different type of question. That's real-time race strategy. So imagine that you are driving on the racetrack, you're going 150 miles per hour, and you need to know, should I make a pit stop now, or should I wait till the next lap? Which choice is most likely to lead to victory? There is no certainty, but there is a strategy that is more likely to lead to victory than the other. It's a statistical problem, and it can be solved by simulation. That simulation has to be done in real time because it needs to be updated as the race evolves and as new information comes in. Is it raining? Is the road getting wet? Where are the other vehicles? How are my tires? Etc., etc. So it's a fascinating new type of problem, but it's not part of a well-defined and somewhat separate R&D cycle the way that the design of the engine is. So again, on the left, yesterday's type of HPC, the traditional HPC, probably runs some Fortran HPC code on a static HPC cluster. The well-understood simulations, you could get away with just refreshing to the latest Intel hardware every couple of years, and it's sort of its own R&D process. It feeds into, for example, the car manufacturer's production, but it's somewhat separate from it. Whereas for the real-time race strategy, it's a much more dynamic situation. And these dynamic types of HPC problems, the HPC of tomorrow, often have characteristics like being data-centric, right? What you're doing is you're getting a massive stream of input data. Somehow you use simulation on it to enable a decision or extract information. They're real-time. You have to give back a result, possibly in an interactive way. And the underlying architectures, the hardware, the types of workloads are much more diverse than HPC used to be, let's say, 10 years ago. There's often GPUs involved, and these workflows tend to be more integrated with the overall product, the overall working of the enterprise or the research project. Next slide here. All right. So let's take a look at an architecture, which is a way that we could do this. At the top of the graph, you see various storage and data stream or data ingestion type of services, from database to object storage to an IoT ingestion service. That's where your data would come in. Cameras that are filming what's going on in the race, sensors on the car that tell you the state of the engine and the tires, and et cetera, et cetera. That's all coming in. Then as we go around the graph, we see serverless, which is serving as kind of an event engine. And then we go to the big white box in the middle of the graph, which is the actual simulation engine. And that is a Kubernetes cluster. So we are going to statistically simulate lots of different race scenarios. For example, you could do it with Monte Carlo. Each of those scenarios is going to be its own container. Now I need to be able to increase the number of simulations that I'm going to do throughout the race as needed. And containerizing the problem gives me the ability to scale up and scale down the amount of simulations very, very fast and very reliably. Another thing that we can do, if you look at the fine print here, is we're using ARM processors here. And we're doing that because these ARM processors are not only powerful, but they're also very cost effective. And this allows us to do the simulations and make race decisions very cheaply. Well, why is that important? Well, every project always has some kind of cost constraint. If you're in academia, then it's the amount of money in your research grant. If you're in enterprise, then it might be your R&D budget, or it's related to your profit margin on your product. Here, however, we're in a sanctioned sport. And so for reasons of fairness, there is a fixed budget that you're allowed to use, a fixed IT budget you're allowed to use during a race to ensure fairness. And so that means that you want to spend your limited dollars as efficiently as possible by using cost-effective processors and by right-sizing your compute solution exactly to the need. That means that you can use your money to make your simulations as accurate as possible, including as many variables as possible, as many statistical parameters, and thereby making the best decisions and hopefully winning the race. So this is all very different from a traditional HPC problem, like designing a car. Now, you see that in various other industries as well. For example, on the right is a soccer game. And so sports analytics are present in pretty much every sport now. They're commonplace. It's a similar pattern. As the game unfolds, you're going to run simulations for who you think is going to win the game, or how aggressive or dangerous a certain action on the field is. Display those statistics for the viewer. So again, that's real time. It involves a high volume stream of data and a significant amount of compute to process that and feed insights back to the recipient, let's say the audience at home. Or on the left, financial services industry also does a lot of similar statistical simulations based on real-time data. It could be updating asset allocations in portfolios, evaluating risks, or ensuring compliance with financial regulations. So it's a common pattern. Okay, now, given that we are in a much more complicated and much more fast-moving, fast-evolving landscape than we were 10 years ago or 20 years ago, there would be great value in also having flexibility in your approach, in your infrastructure, in your software, in your overall architecture. So if you were going to do what you traditionally used to do, buy hardware, fill up a data center, and then go with that for 5 years and not have any ability to adapt during that time period, there are actually significant drawbacks and costs to that. Let's look at a few examples. Well, when COVID hit, of course, research went into overdrive to try and understand this research. The example here shows a billion atom multi-scale molecular dynamics simulation that was used to understand the behavior of the COVID virus inside the human body, like that dark green layer on the outside, that's actually lung fluid. So that was part of the simulation. Now, after a while, though, and that work, by the way, won a special Gordon Bell Prize for solving a valuable problem, but also for integrating HPC and AI in a very effective way. Now, later, when we understood that airborne transmission was very important, we needed to go back and redo these transmissions, and the University of Bristol did some of that work. They took the molecule that had been developed earlier, the model of the virus that had been developed earlier, but now subjected it to a lower pH value, to a different kind of surrounding, because when the virus is in a little droplet traveling through air, that's going to change the pH that it surrounds it, and that will change the behavior of the virus. That presented a new need for the University of Bristol, a need for a large GPU cluster to solve the simulation. They didn't have that. The way they did that was by coming to the cloud, getting such a cluster, and then running through the entire simulations in 2 days. And that was also possible because cloud providers, as well as national computing centers, offered a large amount of compute cycles back then to the community for the common good. Another related example. So what you see here is how the demand for certain types of services and goods just plummeted. And then depending on what you were looking at, partially recovered, wholly recovered, or more than recovered over time. So if you were in an affected industry and what industry wasn't affected, it would be very valuable to be able to scale your resources and your expenses to these very significant market evolutions. Whereas if you had a static data center that you owned, you would not be able to react to that. If you had what I'm calling here an organic data center, a data center that can evolve and adapt to changes, then your business could follow this flow. Next example, there's a big opportunity in the quickly diversifying hardware landscape out there. So let's say that you are in genomics, you're analyzing DNA. Well, there's different methods for doing that. You could use GATK or Centeon, but you'd probably want to run those on a CPU. Or you might want to use Parabricks, but you'd want to run that on a GPU. So if you want to have access to all the available methods, you already need multiple types of hardware. And it gets more sophisticated than that, because if you look at the graph at the top of the page there, you see a genome analysis benchmark that was run on ARM hardware in red, on AMD hardware in green, and on Intel hardware in blue. So as you can see, depending on whether you're optimizing for turnaround time there, for speed, or whether you're optimizing for cost efficiency, you might want to run those workloads on a different type of hardware. So it's a benefit to have a data center that can evolve, that's organic, that can allow you to put all workloads on the most effective type of hardware. It's not just hardware, also the software and the applications, of course, are evolving rapidly and presenting a lot of opportunities. We know that ML adoption has been on the rise for quite a few years now. That's not a new topic anymore. But what we are seeing recently is that there are now many companies that are doing large-scale parallel GPU training on large GPU clusters. That's a new trend. For example, GPT-3 language training, language modeling is one of them. And the illustration there gives you an example of just how sophisticated these models are getting. So they are now becoming so skilled that they can respond to situations that they weren't explicitly trained on. For example, on the right there, this AI might have been trained on the language as well as on recognizing a carpet or recognizing a wine glass, but it wasn't trained on the specific combination of these factors. Yet you can ask it, I have a problem, what should I do? In this case, it tells you that you better get your carpet cleaned, right? So these kind of multi-GPU parallel training workloads will expand in popularity, and ML will also continue to become more contextualized, as you kind of see in this example. Add on top of that the cost of keeping old hardware around and running it is often underestimated. If you look at the graph in the lower right, you will see in the yellow color how many more jobs you could run each year if you always upgraded to the latest hardware. And after a couple of years, the compounding effect of that is just absolutely massive. And so keeping old hardware around for 4 or 5 years is actually very, very expensive. Again, an organic data center that allows you to keep up with the latest and greatest has great benefits. And so when you put all these examples and characteristics of an organic evolving data center together, then as a person representing a cloud provider, I would have to say that, in my opinion, the cloud is definitely one way to build yourself an organic data center that will evolve with external events, market conditions, new opportunities, and allow you to be flexible, agile, and optimize your time to market and your cost efficiency. Now, maybe just a quick word about Oracle. So Oracle is very well known, of course, as a database company, as an enterprise solutions company, and as such, it's had decades of working on harvesting information from data. You could say that's our overarching mission. Now, we actually also have a long history in HPC. So most famously, we bought Sun Microsystems about, well, I forget how many years ago, maybe 10 or 15 years ago. And as such, inherited a lot of HPC infrastructure and a lot of HPC know-how that we've been building on ever since. And we're also a cloud provider, and so we're also offering high-performance computing services, AI/ML, data analytics, cloud services as well. Some more examples of harvesting information from data. The left example, AgroScout, is using drones to overfly agricultural fields, spot pests, plant diseases or insects, identify them, and then be able to react and address this problem quickly so it doesn't spread. And so you also have to use only minimal amounts of insecticide or pesticide. So obviously you have the drone, you have an image recognition aspect of that, data ingestion aspect, model training, and so on. The example in the middle is very, very similar. Kinetica uses flying drones as well as sailing drones to spot garbage and oil spills in water, and then use the sailing drone to go and clean them up. And finally, on the right, CERN, of course, is the particle accelerator in Europe. It's a very complicated and very unique instrument. It has a very complicated control plane that has to be run in an extremely reliable and sophisticated way. And that's another typical type of problem that actually I'm not going to go into, but I'm gonna discuss a related problem here on the next slide. So when you have a very complicated system like CERN or like a nuclear plant or a data center, it's extremely important that you detect problems as soon as possible so that you can remedy them in maintenance rather than having to shut down this massive asset or even lose the assets, which would be extremely expensive and disruptive. And one technique for doing that is what's called the digital twin. So how does it work? So let's say you have your nuclear plant. First, you're going to put sensors all over that plant so that you can monitor exactly the temperature, the pressure, all sorts of properties of that plant. Then you're going to take all that data, all the real-time data, all these sensors, you're going to ingest all that data. Now, the problem is, how do you now know, how do you analyze that data, and how do you know if something is wrong or not? The sophisticated way to do that is to work with a so-called golden asset. So the golden asset is a version of it, is a plant or an engine part or a data center that you know is in perfect condition. And you are going to monitor that one really accurately for a while, monitor all the sensor inputs, and build a machine learning model on that. And that's your digital twin, this digital representation of the perfectly functioning asset. And then the next thing that you need is a sophisticated machine learning technique to compare the two signals, to compare the golden asset as well as the real production asset. And now there are always going to be differences because there's going to be all sorts of statistical noise on every sensor that you ingest. And the more sensors you have, the more complex this data problem becomes, right? Now, in a single server, you might have a couple hundred or a couple thousand sensors. In an airplane, you might have 50,000 or 100,000 sensors. In a data center, you might have 1 million or several million sensors. So these are massive real-time data problems that come in. You're going to have all sorts of little discrepancies between the real-time asset and the golden asset, and you have to figure out which ones are a problem. So MSET, or which is short for multivariate state estimation technique, is an algorithm that's really good at that. It can handle millions of sensors. It can pick up very small disturbances that are no larger than the statistical noise. And it can do this with a very low rate of false positives, false negatives. It's better than neural networks or other techniques for that. And it's a technique that Oracle has invested in and holds patents around and has solutions been built into our cloud platform, into database offerings and data science offerings and what have you. On the right there, you see a visualization of sensor data, of a pressure sensor coming off of an airplane engine. And the red there signifies pressure rising somewhere higher than you'd consider normal. And so something is wrong there. You want to get ahead of that. You want to investigate that engine and maintain it as soon as possible. So some derived applications that you see listed on the slide there is things like remaining useful life. So let's say that you see a sensor indicating that a part is starting to behave outside of the normal range. Now, if you have some familiarity with how that part degrades over time, you can estimate from that how many useful hours or weeks or years are left in the lifetime and when you should go have it serviced. This is obviously extremely valuable information. Predictive maintenance is another word for that, right? As the world gets covered much more and more densely in sensors, as we get more and more IoT dense sensor environments, these kind of methods are going to be more and more important. And so to go back to where we started to talk, it's clear that this is data-driven. It's clear that this is real-time. It's clear that it combines machine learning and simulation components. There are significant compute steps both in the initial machine learning training, and that training has to be updated over time, as well as in the analysis of these potentially millions of data streams that come in. Other applications of the same technique are in detecting counterfeits. So the world loses hundreds of billions of dollars a year in counterfeit parts in data centers. Something like MSET can immediately pick out those fake parts. Here you see a test on the top right of when a counterfeit memory module was inserted, and so that gets picked up on immediately. You might also want to know that to make sure that there's no spyware inserted in your data center, or just simply to detect problems. Right? We saw a case recently or a few years ago of a very expensive data center where motherboards had an occasional malfunction, and no traditional technique, no traditional monitoring mechanism was able to understand why. And MSET almost immediately recognized that there was a problem in some power supplies with a small voltage fluctuation that wasn't enough to traditionally be considered a problem, but that caused a malfunction in the motherboards under some circumstances. And so not only did that minimize the downtime or the disruption in the data center, it also pointed to a very cheap fix, namely replace a small percentage of the power supplies in the data center. I believe I'm up on time, and so I'm going to go and skip one or two slides with detail here. I will point out that one thing that Oracle has done a lot of research on here is in what techniques are needed for data pre-processing, right? So you have these millions of sensors. Some of them are going to be low resolution, or sensors are going to drop out or misbehave when you're working at this scale. Sensors often might have a shorter lifetime than the asset that they're protecting. And so you have to know how to deal with that complexity. You have to, for example, be able to distinguish a malfunction in a sensor from a malfunction in the asset. Obviously, you don't want to shut down a data center or a power plant and then discover that it was just a temperature sensor that was malfunctioning. And I believe this, here we see a little bit more detail in that. So some of these techniques are called missing value imputation or unquantized inferential sensing and what have you. So Oracle has done a lot of research into this, holds several dozen patents that apply to these techniques, and has also integrated these methods with its database products, its data science cloud services, and so on, as well as we have some white papers available on this material on our website. The last thing that I'll point out on this topic is that the MSET algorithm also has the advantage of scaling really, really well on GPU. And that's what's enabled the technique to scale out not just to a couple thousand sensors, but to literally millions of sensors and handle that gracefully. And so here you see the graphs here show speed-ups of literally thousands of times of GPU over CPU. That also has some value when we deploy this in an edge computing approach, where we you take a couple GPU servers and ruggedize them, and then ship a certain number of them out somewhere, stack them up, and have a little cluster on site on the oil rig or at the refinery or wherever it is that this monitoring of an asset is needed. And thanks to the excellent scalability on GPU, you can handle even complex systems this way. And with that, I'm at the end of my talk. So I dove right into the applications and the race cars in the hope of making the talk interesting for you. But if we look back and try to summarize a little bit, then I would say that there is a real confluence happening between HPC, AI/ML, and data analytics. It's creating a synergy between data and computation that we haven't seen before. And so HPC is no longer its own silo where you have the HPC cluster that's in its own stage of the R&D process and runs its traditional HPC applications. We're seeing new demands at the infrastructure level as well as at the workflow or application level. And obviously that demands a new response. And I've given some examples of modern architectures of what I called a flexible or organic data center, and of some techniques that can handle the IoT dense sensor problems that are rapidly becoming more and more common. And I would finish by saying that in my opinion, cloud platforms like Oracle's are one solution that is really well adapted to deal with these challenges and take advantage of the opportunities. Thank you very much for your time. And anyone that would like to follow up with questions or comments is welcome to reach out to me at the contact information given here. Thank you.